So welcome, and today I will try to walk you through a little example of deep learning using TensorFlow. Let's jump right in. So the example we will be using is this data set. These are handwritten characters, and it's kind of a hello world in neural networks and deep learning. But apart being kind of an easy example, it is also a data set that has kept scientists busy for the past 2 decades. If you go to the website over there, you will actually see 20 years of scientific publications on this, and we'll go through that evolution in 40 minutes. So let's start. What is the simplest possible neural network you can build to recognize those images? So it's a simple one-layer network. How does this work? You take your images over there, that's an 8, and the first thing you do, you just consider it as a bag of pixels. You put all the pixels on one line. And then on the line below, you have neurons. So what do we call a neuron? In everything we will see today, a neuron is something that does a weighted sum of all of its inputs and then feeds the result through some non-linear function. Okay, that's it. Weighted sum with weights. We will see what those weights are. And then the result, you feed it through some non-linear function, which we will call an activation function. So here, we have 10 neurons. Why 10? Well, we are trying to recognize digits from 0 to 9. So we are hoping that out of those 10 neurons, one will light up very strongly and tell us this is an 8. That's what we are hoping for. We have to choose the activation function appropriately. And for classification examples like here, the one that is very often used is called softmax. So beyond the equation, what it is simply that you've got your 10 weighted sums, and you take the exponential of them, and then you normalize the whole vector. Normalize means you divide by its size, norm. So the effect of that, the exponential goes up very steeply. So the effect of that is that if one of those neurons is slightly higher than the other, after the exponential, he will be a lot higher, and as you divide by the norm, he will end up still with a significant value, while all the others will go down. So it's kind of a soft way of taking the maximum out of those neurons. So now we have to write this as a matrix multiply. So please rewind to your university years and remember what is a matrix multiply. And we are not going to do this on just one image, actually. Let's do a matrix multiply that processes 100 images at a time, or any number. So at the bottom there, you have our 100 images. They're all flattened, okay? It's one image per line. And now let's take our matrix of weights, and using the first column of weights, we do a weighted sum of all the pixels in the first image. Okay, we have the result of our first neuron. Now taking the second column of weights, we do a weighted sum of all the pixels in the first image, and so on, and we have the weighted sum for the second, the third, until the 10th neuron. Now, we finish this matrix multiply, which gives us, and first, and before that, I have to add one more thing, which is that the input of the neuron is the weighted sum, but we also add a constant, which is just an additional degree of freedom. It's called a bias. There is one bias per neuron, okay? We will try to find out what the good value for that bias is later, as for the weights. So now we have our 10 weighted sums for the 10 neurons. We add our 10 biases. And then if we want to finish the matrix multiply, well, we just continue it, and we get all of the weighted sum for the 99 remaining images. Now, of course, we would like to write this with a simple formula like here, but it's just a little quirk. The plus here doesn't quite work. You see, this matrix here is 10 times 100, and this vector is just 10 elements. You can't do a plus between those. Never mind, let us redefine plus. Well, actually, that is the standard way in which this works in data science, and specifically in Python, which we will be using today, and NumPy, which is the most used scientific library in Python. They call it a broadcasting plus, and it's just a slight extension. It means if you can't add those matrices because the size don't match, well, you try to replicate this one as much as possible until it matches. If that works, you can do a plus. It just so happens that is exactly what we want here. Those 10 biases, we want them added on each line. So let's call it a plus. It's a broadcasting plus. And we can write this formula for one layer of a neural network as a simple expression. So let's go through it again. Here we have our 100 images, one image per line. Each image is 28 by 28, which is 784 pixels. We multiply it by our weights, which create for each image our 10 weighted sums. So here we have, again, 784 times 10 weights. Now, on each line, we add our 10 biases, and line by line, we feed this through the softmax function, which line by line, reminder, a line is the 10 weighted sums plus b for our 10 neurons. So line by line, we take the exponential of all the values and normalize. And that is why here, a matrix of 100 lines, one per image, and for each image, we have the output of our 10 neurons from 0 to 9, which tells us which picture was recognized, which number, which digit was recognized. Of course, all of this works only if the biases and the weights are good. So how do we know they are good? I haven't spoken at all about how we are going to determine them yet, but how do we know they are good? This is how you would write it in TensorFlow, in Python and TensorFlow. You see, not very different. So how do we know they are good? When we are going to train this system, and when we train it, we give it handwritten digits, but we know what these digits are. We have labels for them. And so we are simply going to compare what the neural network is telling us with what the label says that this was. So here is a possible label. We encode it like this. It's called 1 hot. It's just a vocabulary. A 6 is encoded by putting a 1 in the 6th box here. Okay. We encode it like this because it looks very much like the predictions that our system is outputting. These are the outputs of our neurons. And here as well, we expect that one of them will have a high value and tell us that this is a 6. So now we have to calculate a distance between those two, which frankly could be any distance. Euclidean distance will work, okay, no problem. But again, for classification problems, a lot of research has shown that this distance, called the cross entropy, is actually a little bit better. So that's the distance we will be using. It's these numbers multiplied by the logarithm of these numbers. That multiplied by the logarithm of this one and summed across the vector. So this will be our quality control function. It's also called a loss function. And now, let's leave mathematics and let's see a demo. Let's try to train a system. So here I'm training this neural network. What you see here are my training digits. I'm throwing 100 digits at a time at this system. And in red, you have those that are badly recognized. But in white, you have those that it has already learned how to recognize from the training digits. You see here the loss function is going down. Okay, our quality is going up. It's the reverse. So this just shows us that the training kind of works. We were seeing this here as well, but here we have it quantified. Accuracy is simply the percentage of recognized digits. And now we also want to test if this neural network is actually recognizing something in the real world. Okay, we are not interested in the test digits that we are in the training digits. We are interested in the digit that I'm going to write tomorrow, because this is supposed to be used for handwritten digit recognition. So we have set aside 10,000 additional digits to test the performance. Here you only see 1,000 of them, so imagine 9 more screens. But I sorted the red ones, the non-recognized ones, at the top. Okay, and a little scale that tells you what is the percentage out of the 10,000 of recognized digits. And lo and behold, with this one layer, naive approach, we are already recognizing 92% of our digits. We have taught the system to recognize more than 1 in 10 handwritten digits. Finally, what is this? So I told you, this only works if weights and biases are good. So this training mechanism actually changes gradually our weights and biases so that the loss function goes down, and after a certain number of iterations, we have quite good performance. What you see here on these two graphs, this is kind of a histogram of all the weights and all the biases in the system. You mostly see that they are changing, and you also see that they are not exploding. They stay between -2 and 2 and -1 and 1 over there. These are just two handy graphs to see that the system is not diverging completely. So, what we have seen here is how to train a system, that you need a loss function that you will try to minimize, that you need to define a model which has weights, which has free parameters, weights and biases, that you are trying to adjust to produce a prediction that is good in terms of the loss function. So let's see how this is actually done now. Here we go. Let's do this in TensorFlow. So now we are diving into TensorFlow and Python. So first, in TensorFlow, you need to define what is called variables. Those are the degrees of freedom of your system, is what you are asking the system to determine for you through training. So in our case, it's the weights and the biases. We say it's variables. We have seen that we have our weight matrix is 784 by 10, that we have seen previously. Our bias vector is 10 values. Then, during training, you will need to feed in training data. For that, in TensorFlow, you define a placeholder. A placeholder means it doesn't have any values yet. I will feed values during training. So just look at the size of this tensor here. By the way, what is a tensor? Okay, in first approximation, it's just a multidimensional matrix. That's it. And here I have the number of dimensions of this matrix. So let's start from the end. This is the number of values per pixel. Okay, we have grayscale images, so it's one value per pixel. It's not needed here, but I just put it in case you had RGB images. This would be three values per pixel. Our images are 28 by 28, and this is how many images we will have. Well, it's not known at this point. It will be known when we actually feed the images, how many we feed at one time. All right, so variables for free degrees of freedom and placeholders for whatever data you will feed during training. Now, this is our model. This is what we have seen previously. There is only one quirk, reshape. You remember our images 28 by 28, but we first have to put all the pixels on one line to go into our model. This is a very simplistic model. That is what the reshape does, okay? It flattens everything on one line. And we tell it, well, I want everything on one line. The -1 here will end up being the number of images. -1 means there is only one possible number, so figure it out. We also need a placeholder for our known labels. We will be feeding images and labels. A picture of an 8 and a label saying this is an 8. A picture of a 7, a label saying this is a 7. And now we compute our loss function, the cross entropy. So we have seen this multiply is an element-wise multiply. We multiply the bits of the label by the logarithm of our predictions. Okay, it's what we have seen previously on this picture here. We multiply the bits of the label by this number, label by this number, and we sum across. So reduce sum is a sum across the vector. So now we have our loss function, and this, look at it if you want to understand. It's slightly more complicated. This is just the computation of the percentage of correctly recognized images for display. Okay, so I won't get into the details of that. It's how many images were correctly recognized. And now we go to the heart of how neural networks work. We tell TensorFlow, well, please use this optimizer and optimize my loss function. What is this going to do? Well, this loss function, we have seen, it depends from our weights, our biases, and also from our images. So what the general learning algorithm does is that it is going to compute the partial derivative of your loss function relatively to all the weights and all the biases. Now, thank you, TensorFlow, for doing this for me. Because remember how many weights we had? 7,000 and something. So this is a vector of partial derivatives which has 7,000 values. Okay, so it's a good thing that TensorFlow does this derivation for me. And it's also a very good thing because it's a very error-prone thing to actually implement by hand. And it's a real formal derivation. It's not a numerical derivation. It's a real formal derivation. So this vector of partial derivatives, what is it? It's called a gradient. And the nice property of a gradient is to point where? Somebody knows where the gradient points? Up. We want to go down, so we put a minus sign on it, and that's our direction where to go. When I say direction, where are we? In which space are we? We are in the space of weights and biases. So if the gradient tells us, well, this is the direction in which you want to go to minimize your cross entropy, it means it just gave me all the small deltas to add to my weights and biases to go to a region where the loss is smaller. So let's add those deltas and go there and repeat, and that is the training. Compute gradient, follow gradient, which modifies weights and biases, compute, pump in next set of images, of training images and training labels. Compute gradient, follow gradient, and so on. Just one last quirk is this one here. If you jump by the whole gradient, that's a bit too much. To take a metaphor, imagine you're in the mountains, somewhere on the top of the mountain, and you're heading for the bottom of the valley. Now, if you have 7-league boots and you make huge strides, you will be jumping from one side of the valley to the other without reaching the bottom. So you need to go slow. Even if you know where the direction of steepest descent is, you need to go slow to actually reach the bottom. So this is just something by which you multiply the gradient before adding it to your weights and biases in order to go slow. It's called the learning rate. All right. What next? Well, now we have to write the training loop. So one thing to understand here about TensorFlow is that TensorFlow has a deferred execution model. All right? Everything we have written so far, everything that starts with TF something, when it is executed, it's not actually producing a result. It's just building a computation graph in memory. When you want to actually run this computation graph, you have to start a session, over there, session, and then to compute a piece of a graph, you go session.run and one node of your graph. So what's the purpose of this? The purpose is not to make your life difficult. The purpose is to allow distributed training. TensorFlow was built with distributed execution in mind, so that's why it has to know everything about your computation graph beforehand, before you start working, because then it can do magic plus boring logistics for you when you distribute the work to different nodes. One example of something that it knows how to do, if you tell it to do one piece of computation here and another one there, since it knows the graph, it knows which data has to be shuffled between those two servers. And the graph is also useful to do the actual formal gradient computation as well. So let's start our session, let's start our loop, and let's do the training loop. So here I'm loading 100 additional training images and labels. I'm running the train step. What is the train step? You remember what is the train step? It's what we got here. This is when we asked an optimizer to minimize our cross entropy, we got a train step. So the train step is actually the thing that computes a gradient, takes a fraction of the gradient, adds it to our weights and biases. That's what it does. So you don't. You loop. You loop until you're happy with the result. It's not infinite. You will see, actually, what we have seen previously here is that very quickly you get into diminishing returns, and you see that it's not worth looping anymore. You see on this example, I had my cross entropy. In the first 100 iterations, it's going down quite nicely, and then, well, it's no point iterating more, actually, from here on. I will keep this going for 2,000 iteration. Could have been 20,000, but you see on the curves that it flattens out. So at one point you stop. So we run this training step, and then everything else here is just for display. So we compute the percentage of correctly recognized images, the cross entropy, so that we can put it on the screen. But the core of the algorithm is this one. Load 100 training images and labels, run one training step. And that makes the weights and biases evolve, and we put stuff on the screen to see if it is evolving in the right direction. Okay? So here is our basic model on one screen. Initialization, variables for degrees of freedom, placeholders for your training data. Here our model. Here our loss function. This is the computation of the accuracy, the percentage of correctly recognized images. Over there, our optimizer, and we ask it to optimize the loss function. And here, in this loop, we take training images and labels and run the training step, which makes our weights and biases evolve until our system is capable of recognizing handwritten digits with a 92% accuracy. All right. So we've seen some of the things that go into the pot when designing a neural network. The cross entropy, which is the usual loss function for a classification problem, softmax, which is the usual activation function for a classification problem, and mini batching. As we've seen here, we are feeding the training images 100 at a time. But is 92% really good? Come on, it's awful. If you were to use this in an everyday system, I don't know, in the post office to recognize postal codes, well, you're missing almost 1 digit out of 10. How terrible can this be? We have to do this a lot better. So it was called deep learning, so yeah, let's go deep. How do we go deep? We simply add layers. So the way to add layers into a neural network is to stack them. And here you have seen these neurons do a weighted sum of all the pixels. Well, it's equally simple for a second layer of neurons to do a weighted sum of the outputs of the previous layer. So that's how you will stack layers in a neural network. Now, we will change the activation function for the intermediate layers. Actually, softmax is really good only on the last layer. And the very usual activation function is the sigmoid, which is a pretty boring function that goes from 0 to 1, but that is non-linear. That's the main property we're looking for. All right, so how do you write this in TensorFlow? Well, first of all, we will need one weight matrix and one bias vector per layer, okay? And it's actually good practice to initialize those weights with random values. So truncated normal is just a complicated word to say random. So we have for all of our layers, we have a weight matrix and a bias vector. And now this is what our model is going to look like. Maybe you recognize this first one, okay? That's exactly the formula we had previously. With X here, the inputs, this is our matrix holding our 100 images. Well, now on the second line, we do exactly the same thing, but as the input, we take the output of the previous layer. And that's it. Of course, we use the correct activation function, so sigmoid on the intermediate layers and softmax on the outer layer to produce something that looks like, you know, a probability so that we can classify our images. Apart from this, I'm not changing anything else to the code. The cross entropy remains as it is. The training loop remains as it is. I just changed the model, and I initialized the additional weights and biases that go into this model. So, if we launch this, first of all, you will realize that the start, okay, it's only 300 iterations. The start is a little bit slow. And it's not so bad on this example, but actually as you go deep, the sigmoid activation function, I mentioned it for historical reasons because it's really the historical activation function for neural networks. But as we go deep, it's not good. And people invented a new one called the ReLU, which is actually super simple. That's ReLU. Yes. Can you hear me in the back? Yes, you can. So this activation function is simply 0 for all negative values and identity for all positive values. How much simpler could it be? For the little story, actually both of those activation functions, sigmoid and this one, come from biology, and it was thought that biological neurons were actually working like this. So if all the synapses were pumping in signal from one threshold of signal, it would start pumping something on its outputs. Well, now biologists think that biological neurons are working more like this. So this is all biology inspired, but we actually don't care about biology. This actually works better for deep neural networks. Why? Well, we will certainly see plenty of articles explaining why. The reality is that someone tried it and it worked better. Okay, no problem. So that's the first thing we do, and as you use this alternative activation function, you see that the start of our learning is much faster, and actually the cross entropy goes down much quicker. So that's one thing that we can do. Then let's push this to 10,000 iterations. So first of all, look at it. 98% accuracy. We jumped from 92 to 98. This is fantastic. But those curves look really, really ugly, really noisy. And you see here the red curve, which is the accuracy on our test data, the only thing that we actually care about, actually goes up and down by a full percent. That's not good. This is actually a sign of what I was talking about with the 7-league boots. We are going too fast. We are jumping across the valley that we are trying to find the bottom of. So we could go slower, but that would mean 10 times slower would mean that our learning takes 10 times more time. We don't want that. So the good approach is actually to gradually decrease the learning rate as we go. And let me show you the result of that. It's quite spectacular. This is what you get without decreasing the learning rate. This is what you get with learning rate decay. Okay, it's a small trick, but it's spectacular how good it makes things. All the noise is gone, and look at the blue curve. Look at it. This is our training accuracy. It's stuck at 100% for thousands of iterations here towards the end. For the first time, we have designed a neural network that has learned all the training examples, and we have 60,000 of them, so it has learned all the 60,000 training examples perfectly. It doesn't mean that it knows how to recognize all real-world handwritten digits, but at least on training examples, now it's perfect. What else? Well, the other thing you see is this here. Kind of weird. The loss is going down on test examples, the ones we care about. On training examples, it's going all the way down. Well, that is normal. We are actually optimizing this one. We are actively optimizing this one. We are not actively optimizing this one, okay? The algorithm is only working on training examples. It never touches test examples. So it's kind of a good thing that the test performance follows, but without surprise, at one point it stops following and goes and disconnects from the training performance. That is a bit of a problem. It's a problem that people usually call overfitting. And if you look up a manual, people will tell you, well, you need normalization, and the standard normalization is called dropout. And dropout is actually a really brutal technique that works like this. You take your neural network, and during training, in each round of training, you're actually going to shoot a certain percentage of your neurons to discard them from your model. So you do this at random at each round. You take a probability, for example, here, 25% probability of a neuron dying, and at each round in the iteration, you shoot 25% of your neurons. Of course, when you evaluate the final performance of your system, you put them all back, okay? You don't evaluate on a half-dead brain. So this technique, this is how you write it in TensorFlow. So there is a handy function that takes the outputs of the layer, and when you add dropout, what it simply does is that it replaces some of those outputs by zeros, and it boosts the remaining ones by something. That's just so to make sure that the total amount of activation that flows from one layer to the next is not changed. But well, that's just a detail. So what is the effect of this? So let's see from the very beginning. We had our sigmoid activation function, okay, which we replaced by the ReLU. So faster start, and we actually got a little bit more performance for it in terms of percentage of recognized images. Then we added the learning rate decay, which cleaned up all these curves, and actually even helped with the accuracy as well. We were at 98.2 peak, and we are now at 98.2 sustained. We still have this problem here. So let us add dropout. Boom. Dropout actually tamed our test loss curve here, which is good. That's what it is for, according to the textbooks. But actually, in this case, well, it didn't have really an effect on the accuracy. So it was a good try. But now let's try to revisit what overfitting actually means. So if you ask the specialists, this is what they will tell you. Overfitting, at the core, is that a neural network has so many degrees of freedom, so many neurons, that you could imagine to store your entire training data set in those degrees of freedom and just recognize that using a kind of pattern matching. Of course, if the neural network ends up doing that, and it will end up doing that if it has too many degrees of freedom, it will be absolutely pathetic in terms of accuracy and performance on real-world data. So in a neural network, you actually want to constrain the degrees of freedom to force the neural network to create internally generalizations, things that describe the training data and that also generalize to data it hasn't seen before. You need to restrain the number of degrees of freedom. The parallel of that is, even if you have a small network, if you have very little data, it will still be able to store it entirely. So you always need a lot of data to train your networks on. And then, if you did everything right, like here, okay, I actually designed this network with maybe a little bit too many layers, but it's not that bad. I have plenty of data, 60,000 training images. And I added dropout, which kind of assures me that even if I had a little bit too many degrees of freedom, dropout, the way it works, the fact that you are killing neurons in the middle, it kind of prevents it from using those degrees of freedom too badly and ensures that, as we have seen, the overfitting, so the disconnect between the test loss and the training loss, is kind of tamed. So we've done everything we could, and we are still stuck at 98% performance. The only remaining possible explanation is that our network is bad. So why is that? Anybody here has identified something that we did at the very beginning that was completely stupid? We did something dumber than earth. Exactly. What is an image? What is a number? It's a shape, it's lines, it's circles, it's a shape. And we just took all the pixels and put them in one bag without any order, any idea of shape. We just threw away all the shape information. That's terrible, and that's why it's not doing well here. So exactly, we need to design a neural network that will actually use the shape information that we have in our images. And those are called convolutional neural networks. They work like this. So here I'm back to the general example of a color image. That's why I have 3 layers of data in my image. And now, one neuron will do a weighted sum of only a small patch of pixels above it. Okay? And now this neuron, I'm going to slide it over the picture. So the first difference with what we have seen previously is that one neuron does a weighted sum of only a small patch. The second difference is that I'm reusing the same weights for all the neurons. It's just one little patch of weights which I'm sliding across the picture to produce my weighted sums. Okay? So now let's slide it over the whole picture. Of course, I need some padding on the sides, but in the end, I obtain as many weighted sums as I had pixels in my original image. Okay, so we could say this is the way of doing a convolutional neural network. But we have one problem here. Look how many weights we have. So 4 by 4 by 3, which is exactly 48. We had 7,000 degrees of freedom previously. 48, that's not going to work. We need more degrees of freedom. So we will simply do this, the same operation again, using a different set of weights and obtain a second layer of weighted sums. And since we are working with tensors, those 2 tensors can be written as 1 simply by adding a dimension here. Here, where 0 will be for this one and 1 will be for this one. And we have here the general shape of the weight tensor for a convolutional layer in a neural network. So let's look at it. The first 2 numbers is 4 by 4. That's the size of the patch. And the last 2 numbers are 3 and 2. That's the number of channels in the input and the number of channels in the output. So now it's very general. It means that now we can actually stack them. Let's stack them. But we still need to solve one problem. Well, at the very bottom of the stack, we want 10 numbers, okay? So we need to boil this information down in some way. And so the traditional way of doing this boiling down was to add a subsampling layer, which is not used anymore, but it's useful to understand because it gives you the idea. The idea is that, you know, this little patch of weights will evolve to become some kind of shape recognizer. The weights will evolve to produce a high output for a horizontal line, and for another patch, they will evolve to produce a high output for a vertical line or for a small circle. And what you do to boil the information down is you take those values by groups of 4, 2 by 2, and you only keep the maximum one, which tells you, well, here above this one, I've reacted strongly to the shape I'm tuned to recognize. So you just take the maximum one and you get that information that one of those shapes is present above. Well, so that was subsampling as it was done before. Today, people realize that if you play with the stride of the sliding, of the convolution, you get exactly the same result, and you can do convolutional networks with only convolutional layers. Okay, playing with the stride means that if you slide the patches not pixel by pixel, but 2 pixels by 2 pixels, you mechanically obtain twice less points, well, 4 times less points in the output. So that is another way of boiling the information down, and that's what we will do. So this is the network that we are going to build. We have on the top there, we have our image. Now it's back to a grayscale image, our real example. We apply a first patch of 5 by 5, and we actually apply 4 of those patches. So you see 5 by 5, 1 channel as an input because it's a grayscale image, and I apply 4 of those patches, which means I obtain 4 channels of values here, of weighted sums. The next layer, now let's go for a patch of 4 by 4. I had 4 channels in the input here, and let's apply 8 of those patches. So I will have 8 channels in the output with a stride of 2, which means that instead of having a 28 by 28 array of values, I end up with a 14 by 14 array of values here. And a third channel, now let's keep the patch size at 4 by 4. I have 8 channels here, so I put an 8 here, and I do this 12 times. So I will have 12 output channels. Again, a stride of 2, which means that from 14 by 14, I go down to 7 by 7. And now I apply a fully connected layer. So a fully connected layer is what we have seen in the previous section. One neuron in a fully connected layer, okay, does a weighted sum of all the values in this cube of values. And the next one does the same, and so on. That is a fully connected layer. It's what we have seen in the first section of this talk. So let's see if this does something better. Well, first we need to implement it. So one weight matrix, one bias vector per layer. The weight matrices have the shape that we have been explaining: size of the patch, number of input channels, number of output channels. Okay, the output and input channels have to match here. So KK, LL, M, and so on. So I have 3 of those. Then I have my fully connected layer, okay? My fully connected layer, the size of its weight matrix is inputs multiplied by outputs. So in the inputs here, I had, that was on the little drawing before, I had 7 by 7 by 12 values to read. These values, this little cube. And in the outputs, well, I decide how many neurons I want. So here I chose 200. So I put 200 neurons in N. And then I have my last layer, which are my 10 softmax neurons to actually produce a prediction. Those are the initializations. And now here is the model itself. So TensorFlow has a handy conv2d function into which you can pass the weights, the weight tensor for a convolutional layer, and it will do the sliding in 2 directions. It's just a double loop. That's all it does. It does the sliding in both directions across your inputs. Don't mind the complex syntax for the strides, okay? I highlighted in red the two numbers that need to be 1 or 2 to get a stride of 1 or 2. You can read the documentation about the other numbers. The padding strategy, so you remember on the sides we need to extend our images a little bit. But well, here they are on a white background, so we add more white background. That's called same. And these are our 3 convolutional layers. Then we have reshape. Why is the reshape there? Well, it's this one. You know, we have this cube of values here, and we need to put it all in one line so that these neurons can use them as inputs. So that is the reshape. Okay, reshape here, and then the same formula as we had previously for one fully connected layer and the softmax layer. Again, I changed the initializations of the weights and biases. I changed the model. I didn't change anything else. The training loop, the definition of the cross entropy, and all that. Let's try. Let's run this. Convolutional, run. Here. So the first thing you're going to notice is that, well, we're asking the system to compute a little bit more, so it's not as fast as it was in the beginning. The second thing you notice is that, look at this, the accuracy, actually in the first 100 iterations, it already shot all the way up to 92. In the second 100 iterations, it's already at 95, and it's not stopping there. It's going up and up and up. Actually, if I'm going to play you the video because it would be a bit slow otherwise. But actually, if you do this for all 10,000 iterations, you end up, over there I have to zoom, you see 99% is over there, and it's edging closely on this 99. But in the end, I get 99.8. Damn it. I really wanted to beat the 99. Oh, come on. Okay, let's beat the 99%. That's kind of a limit. We have to get over 99. So let's do something. And looking at these curves, first, who can tell me that something is wrong, and who can tell me how to make it right? Look here. Overfitting, yes. Look at the test loss. It's going up like crazy. What can we do about overfitting? Shoot some neurons. Exactly. I like that. Let's shoot neurons. Let's apply dropout. What we will do actually is a little bit more than that. It's kind of a general method. When you are trying to find the ideal network for a given problem, it's kind of a method or a trick. Is that to restrain the network until it hurts, until you know that you can do slightly better. That's what I've done here. I know I can go above 99, but actually I have not given it enough degrees of freedom. So from there, I will increase the degrees of freedom a little bit and add a dropout to make sure that it's not going to overfit because of those degrees of freedom. So that's what I will do here. Look, we go first the patches, a little bit bigger, 6655 instead of 5544, and a lot more channels. So I had 4, 8, and 12. I go to 6, 12, and 24. Okay? So that's more degrees of freedom, and I will add the dropout on this layer. On the other ones, I'm a bit cautious with the dropout. There are not so many degrees of freedom up there. I don't want to start shooting neurons up there. Here, I have plenty, okay? How many? 7 by 7 by 24. That's like 10,000 or something. So that's a lot. I can shoot neurons there. So let's see how this performs. What do you think? Actually, let's keep it on video because of the time. What do you think? Let's go. So it's shooting up right there. I have to zoom. Let's zoom in. Come on, zoom. Now you see what's going on. Look, this is 99%, and it's above 99%. We did it. We did the 99%. And actually, if we let this finish, it will end up at 99.3%. The world record, if you go to the MNIST website, is 99.7. So you see here in a 45-minute session, we have actually done the 20-odd years of R&D into this problem, almost to the end. That's not to say that the scientists have been playing around for 20 years. Actually, they've done something fantastic. They have tried everything that doesn't work and published the stuff that works. Fully connected networks, ReLUs, softmax, convolutional networks, dropout. We now know what works, and we now know how to add layers while still keeping our network converging, and that's why we can solve those problems. That's why we can solve other problems like recognizing cats and dogs in a picture. So just to finish, here is what dropout did in this case. So actually, you see, this is without dropout, but it's already with a slightly bigger network and with learning rate decay. So we are already above 99%, but we still have this overfitting problem. Adding dropout, the overfitting is largely resolved, and we just won 0.2 of a percent here, which, if you think about it, we're fighting for the last percent. So 0.2 with just a simple normalization function is huge. And that's all I wanted to show to you today. Thank you. And before you go, TensorFlow is open source, so you can use it. But if you want to run TensorFlow on Google's hardware, you actually have a cloud ML service that is designed specifically for that, fast learning on Google's hardware. And if you don't want to build your own models, we have a couple of pre-built models. We have an image recognition API, a speech recognition API, a natural language processing API, and then Google Translate, which has been around for ages, but which is heavily, heavily based on neural networks today. So all of that is available as an API, but if you have to build your own neural network, you can use this infrastructure to actually speed up this work considerably. Thank you.